My name is Elga Bojko. I'm originally from Albania and now studying here at Schoolcraft College. I will shortly transfer to university to get a bachelor's degree in chemical engineering and a master's degree in pharmaceutical engineering. My long-term goal is to engage in scientific research and development relating to homeopathic medicine. For a long time, the promise of fuel cells has been like a tidal wave that's always a mile offshore. This might finally be changing since the pros of fuel cells finally seem to be on the verge of overtaking their cons. Fuel cells were first created in 1839 by William Grove, a British attorney and physicist. Modern versions started to be developed in the 1950s. NASA began using fuel cells in the 1960s and continues to invest in their research and development. Since then, fuel cells have steadily progressed and found several applications. Now it seems like this big fuel cell wave is finally hitting the shore. The chemistry involved in the fuel cell operations is fascinating and is the focus of substantial university and corporate research and development efforts. In this short showcase video, I'm going to highlight a few of the underlying scientific and engineering features of the hydrogen fuel cells. This toy automobile is being powered by real fuel cells. The fuel used by fuel cells is hydrogen. Hydrogen is by far the most abundant element in the universe and is a key constituent of water. Ironically, hydrogen gas by itself is virtually non-existent here on Earth. Figuring out large-scale production of economical and clean hydrogen is still a major challenge, just the kind of challenge we scientists and engineers like. One such production method is electrolysis. This simple electrolysis setup shows how electricity decomposes water into hydrogen gas that you see here at the cathode and oxygen gas generated at this anode. Here I'm going to use this much more advanced electrolyzer to produce hydrogen. Specifically, this is a proton exchange membrane electrolyzer that's fed distilled water and connected to this solar cell for clean direct current electricity. If this voltage exceeds water's decomposition voltage of 1.23 volts, water molecules will break down into molecular hydrogen and oxygen. You can actually see newly created hydrogen gas working its way into this water trap storage reservoir, while oxygen gas is allowed to escape over here. Looking closely at this electrolyzer, you can see two perforated plates. One is called the anode and the other is called the cathode that sandwich this very special Teflon-like membrane. More specifically, water is fed to the anode where it's oxidized by a catalyst of platinum nanoparticles deposited on larger carbon particles. This platinum, which is a very expensive precious metal, is layered onto one side of the membrane and catalyzes water into oxygen, protons, and electrons. Here's the oxygen evolution reaction taking place at the anode. The liberated electrons flow through this external circuit while the protons migrate through the sandwich membrane, which is a sulfonated fluoropolymer, to the cathode layer on the other side. This membrane is commonly referred to as a proton exchange membrane, or PEM. When it gets wet, the sulfonic acid dissociates, the membrane becomes acidic, and thus allows cations, in this case protons, to conduct through to the other side. It simultaneously prohibits anions, in this case electrons, from passing through and forces them to flow through this external circuit to the other side, where they combine with the protons to create hydrogen gas via the hydrogen evolution reaction shown here. So here's the overall reaction. The hydrogen gas is stored here in this water trap tank and fed to the anode side of this fuel cell, which is basically an electrolyzer in reverse. Its official name is a proton exchange membrane fuel cell. The hydrogen gas is split into protons and electrons, again enhanced by an electrocatalyst of platinum nanoparticles deposited on larger carbon particles to increase the reactive surface area. Here's the hydrogen oxidation reaction taking place at the anode. These liberated protons conduct through the proton exchange membrane to the cathode side. This same membrane again acts as a barrier to electrons, forcing them to travel along an external circuit to the cathode side. This creates the useful current output of the fuel cell. This is what powers the fan or a light or an automobile motor. Meanwhile, oxygen molecules from the surrounding air are channeled to the cathode side, where they react with the protons permeating through the membrane and the electrons arriving from the external circuit to form water molecules. The byproduct of a fuel cell is water. Here's the oxygen reduction reaction taking place at the cathode. So here's the overall reaction. Okay, I'm now going to open this tube and allow the hydrogen gas I've collected to flow to the anode. Check this out. Fuel cells and batteries are similar to each other, are increasingly popular clean alternatives to fossil fuel-based energy sources. They do have some interesting differences. Batteries are currently better for some applications, while fuel cells are better for others. This table provides a rough comparison for their use in mass-produced electric vehicles. There are, though, many other application possibilities as well. No matter what the future of fuel cells looks like, this project has taught me a lot about electrochemistry and other technologies that I will be able to use for many other advanced applications. I hope you also found this informative. Thanks for watching.